Hello, guys. Today, let's observe the quantum world from the perspective of the macroscopic world. From a macroscopic viewpoint, quantum entities exist like mysterious ghosts, completely defying some of our common sense in the macro world. Why is this so? Let's start by discussing a well-known experiment in the physics, the double-slit experiment. The double-slit experiment was first demonstrated by the British scientist Thomas Young in 1801. It was used to prove the interference behavior of light, supporting the wave theory of light. In simple terms, light exhibits wave-like characteristics similar to the ripples in water and can interfere with each other. Before this experiment, many people believed that light had particle characteristics, meaning that light was composed of discrete particles, propagating in straight lines, and exhibiting phenomena like reflection and the photoelectric effect. This double-slit experiment is actually quite simple. As shown in the video, a laser emits a beam of light onto an opaque board with two narrow slits. The light passes through the slits on the board and projects onto a detection screen behind the board. If we assume light behaves like particles, then in the experiment, particles of light would fly through the slits one by one along straight lines. In the end, we would see two distinct light bars on the screen. But what is the actual situation? In the experiment, what we observe on the screen is not two distinct bars, as expected for particles, but rather a pattern of alternating bright and dark stripes. Based on the experiment's outcome, scientists concluded that light exhibits interference characteristics similar to waves. The light coming through the two slits interferes with each other, much like ripples in water, creating a pattern on the screen resembling a zebra stripe. By the 19th century, there was a consideration that the interference pattern observed in light might be due to the sheer number of emitted photons causing interference between them. The question arose, if only one photon is emitted at a time, would there still be interference resulting in the wave-like pattern? So, in 1974, Giulio Pazzi and his colleagues at the University of Bologna in Italy conducted the first-ever single-electron double-slit experiment. To ensure that only one electron passed through the slits at a time, Giulio set the emission rate to 1 electron per second, making the experiment last for about 2 hours. What were the results? Here's a big exclamation mark. How did a single electron exhibit interference? Could it be that the electron split into two before passing through the slits? Okay, let's explain this issue. Some properties of light cannot be explained within the framework of classical physics. Now, please detach yourself from the inherent understanding in the macroscopic world. We need to understand what quantum superposition is. The foundation of quantum mechanics was initially proposed in the early 20th century by Danish physicists Niels Bohr and Werner Heisenberg, among others, who were part of the famous Copenhagen interpretation. However, the concept of quantum superposition was introduced by Erwin Schrödinger. He used the well-known thought experiment Schrödinger's cat to illustrate what quantum superposition is. Schrödinger's cat describes a scenario where a cat is placed inside a closed box with a device linked to a radioactive substance. After a certain time, there's a possibility that the radioactive substance may decay, triggering the device to release poison, causing the cat's death. However, there's also a possibility that no decay occurs, leaving the cat alive. Until the box is opened, the cat's state is unknown. From the quantum perspective, the cat is considered to be in a superposition state, which means it's both possibly dead and possibly alive until observed or measured, reflecting the probabilistic nature of quantum mechanics. Let's revisit the single-electron double-slit experiment. Even when electrons are emitted one by one, they still produce an interference pattern. This occurs because each individual electron, when passing through the slits, exists in a superposition state where it potentially goes through both slits simultaneously. The subsequent experiments conducted by scientists like Giulio Pazzi were actually confirmations of the existence of quantum superposition. Hold on, the story isn't complete yet. The experiment continued. In order to better observe the results of the single-electron double-slit experiment, two cameras were installed in front of the double slits, one on the left and the other on the right. The objective was to observe which slit the electrons were passing through or if there would be any instances of an electron splitting into two. The results showed that each observation by the cameras recorded only one electron passing through, without any observation of an electron splitting into two. However, what was even more perplexing was that what appeared on the screen were two separate bars instead of the expected interference pattern. The original interference pattern vanished. This result was truly mind-boggling. Can you imagine the astonishment and bewilderment experienced by the scientists when they first observed this phenomenon? Nowadays, it's understood that in the absence of observation, such as when there are no cameras, a single electron exhibits a superposition state of simultaneously passing through both slits, demonstrating wave-like characteristics. However, in the presence of external observation, the superposition of the electron collapses, and only one electron is observed to pass through one of the slits, displaying particle-like characteristics. This duality of light, known as wave-particle duality, is a phenomenon unseen in the macroscopic world. In the quantum realm, all particles exist in an uncertain superposition state, but upon external interference or observation, this quantum uncertainty collapses into a single, determinate outcome. We will combine the above content to propose several questions and provide some theoretical explanations. It's worth noting that many of these are currently in the theoretical stage, unverifiable, and not universally accepted. Question 1. Why doesn't the macroscopic world exhibit this kind of uncertainty in superposition? The Copenhagen interpretation suggests that given enough time, any particle will ultimately collapse into its eigenstate when observed or interfered with externally. In macroscopic objects composed of countless particles, interactions between these particles lead to mutual interference, resulting in the collapse of each particle into a determinate state. The macroscopic object, formed by countless collapsed particles, lacks superposition and thus remains stable. This disappearance of superposition is known as quantum decoherence, where the original coherence of a quantum system, containing superposition, gradually diminishes as it interacts with the external environment. Question 2. What is the theory of multiple universes in quantum mechanics? Take the example of Schrödinger's cat, where the cat remains in a superposition of alive and dead states until the box is opened. Upon opening the box, decoherence occurs, resulting in one world where you observe a living cat and another where you observe a dead cat. Two parallel you emerge in separate worlds. This branching continues for each outcome dictated by different states within the superposition, creating branches of worlds where there's no correlation or information exchange between them, forming countless parallel worlds. Indeed, the quantum world can sometimes feel like the supernatural. We will see if there are more to discover in future. Okay, that's it for today. See you next time.